Good evening, everyone, and welcome to the Kubernetes and OpenShift India April 2021 meetup. So I welcome you all to this meetup. It's great to see all of you here on a Friday evening. Today we are going to continue on the previous month's theme of operators. So while we saw last month on what are talks on introduction to operator, what an operator is, and how do you write a simple operator, right? So this month we are going to be listening from Jakub and Manuel. So they're going to take us through a few use cases of operators and a few community operators as well, right? As we are already a few minutes late, let's kick it off immediately. I'll start off by introducing our first speaker for today. So our first speaker for today is Jakub. So he works at Red Hat and he works on a lot of stuff around Kubernetes. And he's been working in the software industry for 14 years now. He's worked with a software house, a travel software company, a Swiss bank, ad tech company, multiple different kinds of careers and multiple different kinds of work over the past 14 years of his career, right? So I'm sure he has a lot of experiences to share with us. He also, for the last 12 years, co-organizes GECon, which conference, which is focused on Java and JVM technologies. And today he's going to talk to us about Operator SDK use case, which is virtual machine import to KubeVirt, right? So without taking any more time from you, over to you, Jakub.
Hi, thank you very much for introduction. So I will just skip over the first two slides and go straight to the main part of the presentation. So the agenda for the presentation is as follows. For starters, to establish context, I will explain a few keywords that I will be using throughout the presentation. Next, I will talk about the Operator SDK and how it can be used to build Kubernetes applications in Go. Afterwards, I will explain what the virtual machine import operator is and how it can be used, followed by a demo. When you're familiar with VM import operator functionality, I will go over the operator's design. Before we wrap up, I will show you the benefits of the VM import operator by demoing how virtual machine import could be done without it. After all of that, I will move to a short summary and finish with my answers to your questions. Without further ado, let's move to the keywords, starting with OVirt, which is an open source distributed virtualization solution that was designed to manage enterprise infrastructure. And OVirt manages KVM-based virtual machines. KubeVirt, on the other hand, is an open source technology that allows KVM virtual machines to be run as Kubernetes pods. CDI, Containerized Data Importer, is a service designed to import virtual machine images for use with KubeVirt. CR stands for Custom Resource, and that's an object that extends the Kubernetes API. CRD, it's a description of a CR, like definition of custom resource. Controllers are programs that observe the state of the cluster and make sure it is in a desired one. Operator is a piece of software that is capable of managing stateful applications or processes in Kubernetes. That's a piece of software that automates work that otherwise would have to be performed manually by a human operator on a system. For example, database deployment or configuration of a larger scale system or handling upgrades of those systems. Operator is a specialized controller that is focused on its own CRD. Hyperconverged cluster operator is responsible for deploying and controlling KubeVirt and several related operators. You can think of it like as kind of meta operator for deploying other operators building whole KubeVirt ecosystem. And let's talk about the Operator SDK. Overall, Operator Framework is a CNCF incubating project, and it is built upon three pillars: Operator SDK, which is a development kit for building Kubernetes applications. It provides high-level APIs, abstractions, and project scaffolding, which is very handy while you want to bootstrap your project quickly. Operator Lifecycle Manager that facilitates management of operators on a Kubernetes cluster, and Operator Hub that is a place for sharing operators built by community. Operator SDK hides a lot of Kubernetes-related complexity, especially one related to objects management, access, and monitoring. The SDK provides scaffolding, as I mentioned before, and it can prepare a working operator that only needs to be updated with resources definition and domain-specific logic that has to be put in gaps left in the code. There is no need to dig into infrastructural code until it's really needed. The logic encapsulated within an operator is executed in a reconciliation loop that starts when there is a change to an observed resource. The responsibility of that code is to find what changed and what is the new desired state of a managed resource, to perform actions to move the managed resource towards the desired state, and finally break the cycle when everything is in expected state. Use case for an operator could be managing lifecycle of a system of multiple interconnected subsystems. Let's imagine a system of 2 multi-instance applications communicating through some messaging system, and one of them using a database. It could be deployed on different kinds of infrastructure and managed manually by a human operator equipped with tons of automation scripts. And the system is about to be migrated to Kubernetes. So it can look like that and be manageable. One option is to modify existing scripts and still execute them manually, or create a software operator that can perform any operations human operator executed. For example, creating deployments with images in desired version and numbers of instances, plugging in storage for DB and messaging, letting the applications know about each other, so some kind of service discovery, and making upgrades of the components. How to start working with Operator SDK? I know that should be a quick recap because it's been discussed previously during this meetup. So first, you bootstrap the operator project with simple Operator SDK init command. You generate a stub of an API using Operator SDK create API. You fill the generated model with whatever you need to be there, something that's related to your domain. Then you generate manifests and some boilerplate code that's based on the code you just put in there using make manifest generate. Then you create the reconciliation code, and then you can run it like using make install run on a Kubernetes cluster you have available. Of course, you can also build images with your operator. You can publish them, you can deploy them directly in the cluster using Operator SDK's functionalities. Let's have a look at the virtual machine import operator. So the virtual machine operator is a Kubernetes operator that is able to import compatible KVM and VMware-based virtual machines into that cluster where they would be run by KubeVirt. Saying compatible is important, and not all options that are available in vanilla KVM hypervisor are available in KubeVirt. The operator takes care of checking the source VM configuration and reports its findings to the user. So it performs kind of validation of input that user wants to provide. The virtual machine operator was written using the Operator SDK in Go. And let's have a look at the environment of the VM import operator and its collaborators. As mentioned earlier, the operator is deployed in a Kubernetes cluster and it's deployed in 2 pods. VM import operator and VM import controller. I will describe the roles later on. It reads or creates cluster objects like secrets, config maps, storage classes, pods, or network attachment definitions. The operator creates virtual machine objects, which are supervised by KubeVirt. They are defined by KubeVirt provided CRD. And CDI, in turn, is used to transfer disk images to Kubernetes storage. The last system that takes part in the import process is the source, OVIRT or VMware, that manages the imported machine. VM import operator reads metadata of the imported VM, requests shutdown of the VM at source for the import process, and startup in case of an import failure. CDI in turn connects to OVIRT to download the disk images and stores them in Kubernetes storage. Let's have a look how virtual machine import with our operator works in practice. So for the purpose of the presentation, I created a virtual machine in OVIRT. That virtual machine has its own ID. We'll use it later on to start the import. That virtual machine has one network interface, and it's using network APS and network unique profile APS. It's got one disk, and it's the boot disk with the operating system. And we can connect to that virtual machine from OVIRT. And we can leave kind of message for ourselves there to see that we can read it on the other side from VM running in Kubernetes. So there is nothing in the home directory. Let's echo hello to hello file. That's a specific date. And now we can go into editing YAML files. First one is a secret that defines connection information to OVIRT. So we have API URL, username, password, and CA certificate that we will use to validate the certificate provided by the server upon connection. Next, we need to have virtual machine import CR. And that CR references the secret I just shown. So it's known to the operator where to look for the credentials. We can specify the name of the virtual machine at Kubernetes cluster, whether it should be started upon import. And then we provide information which actual VM has to be imported from OVIRT defined in the secret. So that's the ID that we've seen in OVIRT console. We also provide mappings of two kinds of resources for network and for storage. So we need to tell VM import operator which storage class to use for the disk and which network to use for its network. In this case, it will be standard storage class and pod network attached to the virtual machine. So we create our CRs. And at that point, the import started. We have that object already in the cluster, and we have the status part populated with information that the validation of the VM and the mapping completed successfully. And here we see that the VM at the source is down. So the data copying started. At this point, CDI transfers the data from OVIRT, and here we can track the progress of the data volume CR that is managed by CDI. it's done after quite some time. And at that point, we can have a look again at the virtual machine import and see that the virtual machine is ready and the import succeeded. So we should have virtual machine and virtual machine instance in the cluster. So that's the virtual machine instance running, having IP assigned, and we can connect to it as well using virtctl tool and VNC protocol. So we've got the same login. And there the file that we've left should be present. Yeah, there is the file. And one with January date. After you've seen what the operator does, let's have a closer look at how it does it. So, as I mentioned before, the project comprises of two single container pods, VM import controller and VM import operator. VM import controller pod is responsible for executing the VM import reconciliation loop. So that's the code that manages the whole import, connects to the OVIRT, connects to the create virtual machine, CRs, and so on. VM import operator's responsibility is managing lifecycle of the VM import controller and all related resources. So CRD, service account, role binding, deployment, and services. So basically, VM import operator deploys VM import controller, and using specific configuration CR, we can upgrade the controller or change its settings through the VM import operator. And what's important, thanks to that operator, it is that part is compatible with HCO and can be part of that big KubeVirt umbrella. The operator, VM import operator, uses Controller Lifecycle Operators SDK. That's a mouthful, but that's a library that was created from code developed by the CDI developers for the needs of their own project, because they also have an operator that manages their own CRs. And the code was so useful and applicable in other scenarios that I've extracted and modified it to create the library and use it in the VM import operator. And in fact, using that library gives an operator compatibility with HCO requirements. And the library provides code that manages resources defined by a developer. It undertakes proper actions when creation, removal of, or upgrade is requested. If one wanted to implement operator that manages multiple resources and makes sure that their configuration is always correct and allow for updating them, for example, upgrading version of a container within deployment, one would have to spend a lot of time implementing tedious state machine code. And the library makes it as easy as implementing a few interfaces and using provided structure in the reconcile method. If one needs to have many separate applications managed in a similar way, and the Controller Lifecycle Operators SDK is a thing to use in each of these operators. Library is extensible, so it can be applied in very different use cases. And the library consists of several packages that can be used together or separately. API package defines common types and constants that are required by the other parts of the library and that are compatible with HCO. SDK package provides several helper functions used in the other parts of the library. Callbacks package provides callback registration and dispatching facilities used to execute additional resource management logic in predefined places in the reconciliation loop. Resources package provides resource definition helpers for creating them with only a few method parameters. It can remove a lot of boilerplate related to creating deployment, services, and other types of resources. OpenAPI package provides OpenAPI definition of the common status structure, and reconciler package provides the reconciler structure responsible for executing lifecycle reconciliation. Developers who want to use the reconciler have to provide a resource type definition that makes use of SDK provided status type, which describes the life cycle or life stage of the managed operator, like this one. And implementation of a following interface, where most of the methods take the user-defined CR as parameter, is also required. And they're mostly one-liners, as you will see in a moment. And here's an example of an actual status definition making use of the SDK type. The code comes from a reference implementation of an operator using the SDK. I invite you to have a look at it and see how simple it is to create an operator that can oversee multiple resources. So we just inline status structure within our own status definition. And CR manager methods, as I mentioned before, are mostly one-liners, except for maybe get all resources method, which provides instances of the managed resource object. So it will be as big as many resources you want that operator to manage. And after the overview of that infrastructural part of the operator, let's have a look at the domain side of it. The virtual machine import is a namespace custom resource that defines the source of the VM, the identifier of the VM on the source, and the mapping to be used for the import, as you've seen that during the demo. Second one is resource mapping, which represents network and storage mapping from external VM provider to KubeVirt. And you've seen in the demo mapping put in line inside the virtual machine import, but it also can be provided separately as a separate object. And the third part is plain Kubernetes secret that defines the credentials to the OVIRT provider or VMware. Let's have a closer look at the virtual machine import CR. There are, of course, the metadata, the name and the namespace. For that CR, there is the reference to the secret defining connection information to the source provider. There is reference to the external resource mapping. So that's what I mentioned. You can put that disks and network interfaces mapping to an external CR and reference it here. And it's in the resource mapping where you provide name and namespace. The target VM name that would override the name of the virtual machine when it's created in KubeVirt. By default, it's a derivative of the virtual machine name in the source. We can specify whether we want to start the virtual machine after import. We might want to choose to keep it down after the import for some reason. Further, there is the reference to the source of your virtual machine and the mappings. In this case, you can see disk mappings that can be provided only at the level of the virtual machine import. Because they are very tightly coupled with the virtual machine that is imported, it makes sense to have it only here, not to externalize it anywhere. Where you can map specific disk ID to chosen storage class. And resource mapping CR is not reconciled in any way and only complements the virtual machine import CR by providing mapping between network and storage resources in the source environment in Kubernetes. Source VM network interface can be mapped either to the pod or in a number of networks defined with network attachment definitions in target cluster, which are managed by Multus CNI plugin, which is supported by KubeVirt. So the network attachment definition needs to be configured beforehand. If you don't have that in your cluster, the import would fail because the mapping is incorrect. It cannot map something to something that doesn't exist. So at this level, storage can be mapped from storage domain in OVIRT to storage class. You cannot put disk mapping at this level. And the purpose of that resource mapping is when you want, for example, migrate tens of virtual machines that connect to the same network, use the same storage domain, and you don't want to make all those VM import YAML files big with one and the same mapping. You can just reference one common mapping, change it later on if something's wrong, and it would work for all virtual machine import CRs that reference it. And following secret is required to contain source provider API URL. In this case, it's OVIRT, username, password that are used to connect to the API, and CE certificate that will be used to validate the server we're connecting to. And let's go over the VM import flow. So first, the user creates a virtual machine import CR, which you can see in the left top corner of the diagram. Next, the virtual machine import controller retrieves the configuration of the source VM from the source provider, validates the CR and the VM, and stops the VM at the source provider. In the next step, the virtual machine import controller creates a diskless KubeVirt virtual machine. Afterwards, the virtual machine import controller creates a data volume CR for each VM disk in the source VM. So based on that, the CDI controller creates PVC using specified storage class, and spawned importer pod connects to the source disk and streams it to the persistent volume. So after it's done, we have all of our data back in, we have in the cluster. And in case of VMware, there is a need to convert the imported disks using V2V tool, and that job is executed by a conversion pod. Because as I mentioned before, KubeVirt manages KVM virtual machines, and they are different than the ones used by VMware. Finally, the new virtual machine is started if the source VM was running or the user instructed the operator to start it. And after all of that, the virtual machine is usable. So that's basically how what I've shown in the demo before looks like during the reconciliation. Let's see how that VM import would have to look like if the VM import operator wasn't around to help with that. So another demo. First, we need to create a few resources, starting with a config map for the CDI controller that describes or provides the CE certificate of our OVIRT server. We need to create data volume and describe that data volume with access mode, the sizing, and information about the OVIRT provider. So we provide URL, disk ID, reference the config map I've shown before, and a secret that we'll create in a moment that contains the username and password to that OVIRT cluster. So we create the map, we create the secret that will be used by data volume. Here we provide username and password. Now we create the data volume. At this point, the data transfer started. We haven't created virtual machine yet. We're just moving the data from OVIRT to Kubernetes. And we can track it exactly in the same way as with the operator. When it's done and we have the data in the cluster, we can create virtual machine CR. That's a KubeVirt CR, which is much bigger than the virtual machine import CR. And we need to provide a lot of configuration options describing the VM. We need to reference the data volume we've just created. So the virtual machine would have the OS that we've transferred. So we create the virtual machine, and now the KubeVirt will start the virtual machine instance. Again, we see VMI CR running, having IP, and we can, in exactly the same way, connect to it using VNC and show the same file that we've created in OVirt to confirm that's the same virtual machine that we've been importing. And what's important here is that the whole virtual machine CR is big. It has to be carefully crafted to map the virtual machine in running in the other provider. So we have to describe correctly the CPU and the memory. We need to adjust the sizing of the disks that are attached to that virtual machine. Then do all that we've done and have the virtual machine in the cluster. But imagine how it would have to look like if you had tens of virtual machines to import and you would have to manually create different configurations that virtual machine import operator detects, basically basing on the source configuration. And after the talk, you should have awareness of the VM import operator and how it can be used to help with infrastructure migration from virtual machine-based one to a container-centric one, Kubernetes. And the information provided about the Operator SDK and Controller Lifecycle Operators SDK should allow you to start working with them to address your specific needs that you can face in Kubernetes. Thank you very much. And do you have any questions?
There was one question about how the events for VM up and down will happen. Like, very clear to me, but I'll read it out. How the events for VM up and down will happen, which will be used.
Okay, so when we start the virtual machine import, we read the data from the OVirt cluster and we hit the API. There is a specific endpoint telling the OVirt to shut down the virtual machine. So at that point, we're polling the OVirt server, trying to get to the point when the virtual machine is down, actually. So if it doesn't end in specific time, we have to fail the virtual machine import. So does it answer the question?
If you have, folks, if you have a question to ask directly, raise your hands. We'll
you can raise your hand and we'll unmute you if you have questions. We still have about 5 minutes.
What do you mean by that question? Would these can this fit in the cross-plane landscape, like cross-platform maybe?
Yeah. Hi, am I audible?
I can hear you.
Yeah, so crossplane, like I've pasted the link. It's a project that which enables platform teams to assemble infrastructure from multiple vendors, and it exposes higher level self-service APIs. So would this be like an operator which can fit under the Crossplane project?
I'm not aware of that project. I haven't been aware so far, but from your description, it sounds like something that can be used. For now, the VM import operator is used by other project for mass virtual machine migration, and it's called conveyor forklift. That's like a one layer above virtual machine import, and you can specify loads of virtual machines that can be imported. But I will have a look at that Crossplane project.
Okay.
So
yeah, thank you.
Yes, so I think that's all the questions that we had. So in case you have any more questions, we got one more question, and I think we have time for it. So the main benefit to use operator and overt is the question. So,
okay, so the basic use case for the virtual machine import operator is to allow users to migrate the infrastructure from a purely virtual machine based managed by OVIRT and move them to Kubernetes as virtual machines, because sometimes they cannot convert their services, their products from virtual machine based to pod based. There can be multiple reasons why it cannot happen, and they need to run as virtual machines, or they need some transition period when they need time to migrate the code to work in Kubernetes natively in pods with containers. So the operator itself, to sum it up, allows the user to change the infrastructure more easily or smoothly, not being worried about infrastructure that's not transferable to Kubernetes.
I think that answers the question. So yes, so now we've come to the end of the first session by Jakub. Thank you so much, Jakub, for taking this time and spending this time with us and talking to us about an interesting topic. I think we have about 5 minutes of break now. So in case you want to, if you have any more questions or anything, you can post it on the chat, and we can begin again at exactly 5 minutes from now. We will begin Manuel's session. Okay? So if you want to grab some coffee or anything, feel free to.
Okay, again, thank you very much for having me.
I have one question, Jakub, for you. Did you mention the operator was written in Java? Okay, if you are there.
Jakub's going to grab some coffee.
Oh, maybe, yeah, true. Because using Java itself for writing operators, that's an interesting use case, because most of the operators are in Golang. and that's more that's generally or ideally it's an ideal language to use with this whole ecosystem. I was wondering like what's the experience like using Java, because yeah.
Otherwise, also it's an interesting. I know it's interesting to know if people have used other languages to face to write operators, like other languages. So, anyone here has used anything apart from Go?
So Avni mentioned in the chat, yeah, since Operator SDK was mentioned, that means it should be in Go. So yeah, that makes sense.
So should I share my screen already?
Sure, yeah.
So I think folks are back from the coffee break. So we can start with the second session. So before starting, I would like to introduce our next speaker to you. So Manuel is our next speaker. So he also works at Red Hat. So he started his working as a software engineer in 2013. And since then, he's worked on multiple projects in big enterprises and distributed software projects as well. So currently he works as a site reliability engineer at Red Hat, and he maintains and automates the life cycle of several OpenShift clusters. So today his talk is something that I was looking forward to. It's an interesting topic. It's titled "The CR That Goes Around in Circles: A Tale of Common Pitfalls in Operator and CRT Design." So over to you, Manuel.
Yeah, thank you, and thanks for having me. Yeah, the title is chosen because it's like one of the most scariest things that can go wrong when you're writing an operator, when you have a CR that just goes around and gets reconciled over and over again, and it just never finishes. So this is basically also the first pitfall we will look into, or there can be several mistakes that you're doing that result in such a thing, and we will discover some of them during the talk. But first, thanks for your introduction, and I think I can basically skip this. You find a bit of contact information in case you want to reach out. You can just shoot a mail or reach out on Twitter. I'm based in Germany, and I love fries, as you can see from the picture. And probably that's the most important information you need about me. So everything we are going to talk about in this talk is based on my personal experience in the past 2 years at Red Hat, where we're in the OpenShift SRE organization are building and maintaining a bunch of different operators. So it means everything I show here is something that I've seen or heard about in one of the operators. But it also means that there may be many exceptions for the practices that I share. So please don't take everything as set in stone. So if I say you shouldn't put something in the spec of the CR that you're reading from, that might be true for many cases, but it doesn't mean that you can never do it, because there may be cases, and there are cases where this is really important and you need to do that. So yeah, it's always depending on the specific use case you are working on. All the examples I'm using are based on Operator SDK and written in Go. So I'm very glad that Jakub already introduced Operator SDK to you. So because I skipped that part mainly. So it's really good that you heard about it already and know what it looks like and know how to use it. So we don't have to spend too much time on that. So probably this slide is good enough for you to see what it looks like to implement an operator based on Operator SDK. When you use Operator SDK, you run a bunch of commands, and what you get out of those commands is a CRD definition where you can add the fields that you need in your CRD, and you get all the objects that you need to apply to your cluster, and you get a bunch of boilerplate code, in most cases in Golang, that you can use and expand to build your operator. And one of the main things that you will see in that boilerplate code is the so-called reconcile function that you see here on screen. This is how it currently looks like when you generate a new operator. And that's basically the main function of your operator. So this function will be called every time one of the watched CRs is created or updated. Every time that happens, Operator SDK will call this function. So everything you write will start, or the most things you write will start in this function and reach out from there. What you need to know about the interface of that function is that when you return an error from the second return value here is an error, when you return an error there, what Operator SDK will do is requeue just the same request to your operator. So you will receive the same thing again and can try again to, probably this time the error doesn't happen because you were waiting for an external thing to get ready or something like that. The result object here can be used, for example, to requeue the request after a certain amount of time. You can say, I want to requeue this after 30 seconds because in my knowledge, that's how long it takes until the external object, like a database or whatever you provision, gets ready. So that's Operator SDK in 10 seconds. We will now look at something that can be put into that function, and the example that we use for that is the famous useless object operator, the useless operator. And I built this specifically for this talk, so this is not a real use case or a real operator or something. You can find it on GitHub, but just so you can go there and inspect the code that I'm talking about here. But all the important things should be in the screenshots that I made. Yeah, so for that operator, I built a custom resource, which is called the useless object. And it's a really useless object because it does nothing and it has nothing. The only thing I do with it in this example here is I basically want to tell the user when was the last time the operator updated that CR. And for that, I created a field in the spec, and that's called last updated at. And I calculate the time and put that time into that field. And then I call the Kubernetes API to update the CR that I just listened in the reconcile loop. But what will happen is probably not what I want to happen, and that's what you can see in this small video that I created. So the example is running on an OpenShift cluster. That's why I'm not using the kubectl command line, but I'm using OC, which basically uses the same syntax than kubectl. You just can use the same things and exchange kubectl by OC here. And yeah, so this is the part where the operator is running, and we will now just follow the logs from that operator to see how the output of the Operator SDK generated operator looks. And then we will apply one example CR that the SDK created for us. We can look at it. There is really not much in there, even an outdated field, but that's not too important for us because we only want to fill that one field, which is the last time it changed. So here I'm now applying the CR, and now take a close look to the right side because you will now see what happens with that thing. And there we already have like the title of the talk, right? It's a CR that never finishes. It's reconciled over and over again. And as we can see on the left side from looking at the spec, what happens is each time it's reconciled, we update the last updated add field, and then we reconcile it again. And why does this happen is what you can see when you inspect the whole object, you can see that there is a generation field, which is updated every time when we update the object. So there is this generation field. You can see this. This is basically the number of times we reconciled this resource already in the few seconds that it's alive. So why does this happen? This happens because when we, in our code, let me go back to our code quickly. When we updated the spec here and updated the object in Kubernetes, what happens is that Kubernetes will see that the CR changed, and what it then does, it creates an event for our operator and tells the operator basically, this changed, you need to reconcile this. So our controller here gets another request in this reconcile loop. We'll again update that field, create another generation when updating the CR, and be called again to reconcile the object. So the first thing, or the first hint I have for you is don't update the spec when you can avoid it. That means you should put as much as you can that's like relevant for your internal processing, or things that are just information for your users, like the date when you last changed the CR. Put that into the status, because that changes to the status won't update the generation and won't trigger a new reconcile when you configure it correctly. And that's because the status is a sub-resource of the custom resource, and those don't trigger changes. So what you need to do for that to work is you need to also ignore the state changes, and that can be done. Okay, so like this is how it should look like. We put, instead of putting it in the spec, we put it in the status, and the rest is the same. We just call another update function here because we only update the status and not the spec of the custom resource. And what we need to do additionally to ignore the changes to the status is we need to ignore changes where the generation of the CR didn't change. This is the number that that you've seen in the video. And that doesn't change when we only update the status, which is a sub-resource. But if a spec changes, this actually changes. So you can use that to make sure that you can update the CR status as you want without getting another run in the reconcile loop. Okay, and I guess this is now, this is how it should look like or how we expect it to work. We need to get a new pod because I had to delete it, and we queried the logs again. Probably I can skip through this a bit. And what you can see now is that I apply that, and I get one message that it has been successfully reconciled, and then it's done. That's how you want it to look like. You want it to have as much reconcile loop runs as you expect it to have, and nothing more. Okay, you will look again at the generation, and then you can see the generation is exactly 1, which is how it was from the creation. And the last status update, like the status update is still there in the status part. Okay, so now what about times when you have to update the spec? What are you going to do then? Because you don't want to continue reconciling after updating the spec, because now you know that updating the spec will create another request for our operator, which will result in another run in the reconcile loop. So what you need to do is when you change something in the spec, at least when you're using Operator SDK, you just return from the reconcile function, because you know there is already another reconcile run in the queue that can then continue from where you stopped. And this example is to show you what happens when you don't return immediately, or what can happen. Like, it's a very dramatic case here that I showed here, but it shows what can go wrong when you don't do it. So in this example, the user CR, which is still very useless, gets a generated UUID added to the spec, and then we update the CR. And believe me, this time we really need to update the spec. This can't go to the status. And what I do then is we call some external API after updating. And of course, when this external API returns an error, we return that error. Now it happens that this external API that we are calling returns errors quite often. Actually, every time we call that function. So how that flow of the application will look like is, I try to visualize that here. There is this useless object, which is first in the queue, which will get reconciled. We update the useless object, which will create another, add another object to our work queue. Then we call the failing API, which returns an error. We return the error, and Operator SDK will put another object to the work queue. So this is what I call an operator fork bomb, because every single reconcile run will just look the same, right? So you have like the work queue will explode. Operator SDK can handle this quite good and creates external exponential backoffs and stuff like that. But in the best case, you get again the CR that goes around in circles, but that's not what you want. So the best thing is, after updating the object here, just return and let the next thing continue the work where you left off. Okay, so, but for that to happen, you might already have seen it in the previous example where I generated a UUID every time reconcile has been running, right? But that's also not what you want to do, because what you really want is, when it's set, we don't need to do anything. We need to discover if our reconcile loop actually needs to do something, and only then do operations, because we need to be aware that at any time there can be a new request for the same resource running in here. And that means that this reconcile function needs to be idempotent. And that's basically what I achieve with this. If, for this simple example, if it's not set, I set the new UUID and return afterwards. And in the next run, which will then start immediately, I see that this is set already, don't do anything, and continue to the rest. Okay, actually, this is wrong, because this line here needs to go in here. But good, you know what I mean. So this is the third item I have for you. You should make sure that the reconciliation is idempotent. And this can be quite easily achieved by splitting up that reconcile function into smaller parts, each representing one operation that you need to do, and which each is idempotent, which each checks if it needs to apply something, does the changes, and then tells the reconcile function if it needs to return or continue processing to the next item, and so on. Okay, here's another best practice for you. You should keep the output resources that you create with the input custom resources when you can. Here's again a picture where I try to visualize what it shouldn't look like. So let's say you have an operator that watches all the namespaces, and you have two different namespaces with each having CRs. You reconcile all the CRs, and for each of them, your operator creates a pod inside a central namespace, for example, the namespace that the operator itself is deployed in. What happens is we need to make sure that we don't create name clashes when creating those pods, because in those different namespaces, there could be objects with the same name. Like here, we have 2 useless objects with the name object1. So what we ended up doing quite often is prefix the output CR name with the namespace of the input CR, so we can make sure that we don't have name clashes there. But that's exactly what namespaces are made for, right? So whenever you can recommend just putting the output CRs into the namespace of the input CR, because then you don't have that problem. You still need to make sure that this pod doesn't exist already, especially if you're creating pods, but it's much easier than having like collecting all of them in a central namespace. Also, it's helpful for your users because they can just look at the namespace they are creating CRs in and see what's going on, and don't need to have the permissions to look into a central namespace to figure out if the pod is configured as they expect it to be, for example. Okay, so this was number 4. Let's go to number 5, and that's about cleaning up. You should make sure that you're cleaning up correctly when a CR is deleted. That means everything that your operator created when the CR has been created should be cleaned up. And that can be done by adding finalizers to the CRs, because with a finalizer, Kubernetes won't delete the object until that finalizer is removed. That means your reconcile loop will be triggered again with the finalizer, and then you have time to clean up everything you created and then remove the finalizer, so Kubernetes will, in the end, remove the CR. For things that you have in the same namespace, however, you can use owner references, and with owner references, Kubernetes will take care for deleting the depending resources. Handling the deletion in the operator itself is a bit more complicated than just using owner references, but in some cases, like when you have something in another namespace, then you can't use owner references, or when you create like third-party resources, for example, say your application or your operator needs to create a RDS database on AWS. Such things, of course, can't be done with the owner reference, and for that you need to use finalizers to make sure you clean everything up, and your users can be sure that no resources are leaked, basically. But at the same time, you should really do your best to make the deletion not fail, because it's really annoying as a user to delete a CR and see it's blocked forever because that finalizer is not removed. And then you're tempted to just remove the finalizer, but then you don't know if there is any resource that the operator created that will be dangling forever, which is a problem. So do your best to make the deletion work. And that actually brings me already to the last point I have for you, and that's when there is an error in your reconcile function in reconciling the CR, make sure that you communicate the error properly to the user and make that visible, because if the first action of debugging something is attaching to the logs of the controller and then filtering out the requests which are actually related to your custom resource, is really annoying. So at the very least, make sure that the error message that last occurred while reconciling is written to the status of the CR. So one thing that I can recommend is just wrapping the reconcile function in, like, you create the reconcile function and the actual reconcile happens in a different function, which I just called reconcile func here. And when this function returns an error, before returning it to Operator SDK, we update the CR status with the error message that occurred. And then we return the error. So as you can see, I ignore the error that is returned by the status update function. That is because just because the status update failed, we don't want to lose the actual error message. And then we return the error to reconcile. Okay, so that will then help the user when investigating an issue because they can just look at the CR and from the status at least see the error message that happened. You can have that be more sophisticating, like adding an actual stack trace there if you want, or producing really good error messages, conditions that tell in which step it failed. But at the very least, you can wrap it like this to display the error message. Okay, those were the 6 things I wanted to share with you. So thanks for attending. I collected some resources here, like blog posts and the Operator SDK Getting Started guide, if you want to get in touch with it now that you heard in 2 sessions about it. And yeah, feel free to ask questions or reach out. My contact details are there again.
That was a really interesting topic, Manuel. So yeah, it made me realize that a lot of operators have written till date are useless. So yes, so if you have any questions for Manuel, you can feel free to raise your hand and we'll unmute you. Right? I think we still have some time. You can also. Yes.
I have one question. So since Operator SDK does so many things, like lot of scaffolding and things like that, can Operator SDK help in this case? Like can there be subcommands or some kind of checks, static checks for code? Like, okay, you haven't taken care of cleaning up or things like that.
Not so far. We've been reaching out to the team, talking about that splitting up topic, because we ended up creating like types to tell the reconcile function what it should do, if it should continue, if the CR changed, and that's what it returns. But it's like the design of the operators are very different, and so it's nothing that you can say is something that can be applied to each and every operator, and that's why it's not done by the SDK, but something you need to care for yourself.
Yeah, makes sense. Okay.
So is everybody now scared to try Operator SDK, or are you looking forward to trying it out? It's really an easy tool. You can get started with building an operator in 5 minutes and have something running on your cluster.
Also, if you have any feedback for Manuel or Jakub, you can unmute yourself.
Thanks, guys, for making this even possible, and thanks for Jakub and Manuel for having the talk. Just since I'm basically beginning on this topic, so sorry for this basic questions. Manuel, like the operator basically means in the previous talk from Jakub, I understood like what it is, but it is the similar lines like the operator use case, which you are also trying to, but these are the kind of practices which you communicated, right?
Yeah, exactly. So as I said, this wasn't nothing that you've seen in code is actual production code or something you should like do in production. It's more from looking at different operators and implementing different operators and running them. That's what I think is good to know before you start writing your operator, and then being surprised that what happens with your CR. So for example, for a long time, when working on my first operator, I was expecting that when I update the status, that there is no requeue of the object, and just did that. But it turns out that happens if you don't explicitly ignore changes if the generation doesn't change. So yeah, it's really to help you get started and probably don't repeat the mistakes that I made.
Just one thing. So can't we have a metric of some sort watching how many generations, like the generation on every generation change? There could be a metric and alert watching if there are so many generation change in 10 seconds, for example. That could be a good way to tackle it, right?
Yeah, so such cases where the CR like reconciles in an endless loop are usually you see them very quickly because the operator starts to get slow and there is not much happening and your CR in the end doesn't reach the state that you want it to be. So in the best case, you already catch that while testing. But yeah, the operator, when using Operator SDK, you also get a lot of different metrics that you can use to build alerts on. So you can have a look at them. I didn't include that here, but there are many metrics exposed, like how long it takes to reconcile a CR, how long the work queue is, and stuff like that.
Thanks. Yeah.
So do we have any more questions? I think we can wait 2 more minutes for the questions to come.
Meanwhile, if people are hiring, they can do a hiring pitch. Nobody's hiring? Okay.
So I don't see any more questions coming. So I guess, and yes, first of all, before we part ways, I want to thank both our speakers, Jakub and Manuel, for taking the time out today and being with us and talking to us about interesting things, especially the common pitfalls of in operator and CRD design that Manuel talked about, and then the virtual machine, the virtual machine import operator by Jakub. So thank you so much, Jakub and Manuel, for spending this time with us on a Friday evening or an afternoon over there. And also, I would also like to thank everyone who joined us, all of you, for making this event possible. We do this meetup every month, and it's great to see folks turn up every month for the meetups. So for those of you who do not know, we do this meetup every month, and we used to do theme-based meetups before the pandemic, but these days, depending on availability of speakers, we do meetups without a theme. So if you want to speak in one of the upcoming meetups, you can get in touch with us for that as well. And yes, I would also like to thank Kinfolk for sponsoring the Zoom for this meetup. And also, if you aren't following us on Twitter, our handle is KTSBLR. You can follow us on Twitter over there. And most of us are on the Kubernetes Slack. So if you haven't joined Kubernetes Slack yet, please join there. We have 3 India-specific channels as well, in -dev, in -events, and in -users as well. So you'll find most of us over there, and you can get in touch with us on the Kubernetes Slack as well with your questions after the event. And yes, so that's pretty much it. If you have any talks or if you would like to speak, if you would like